Section 4.6, we'll begin with problem 16 here. And with all your problems that you're going to graph, you should consider the domain. The domain for polynomials is pretty friendly. There's no place where the denominator can equal 0. There's no place where you can have a negative underneath the log. And there's no place where you can have a negative underneath the square root. So the domain is everything. You can write it as negative infinity to infinity, or you can write it as script r, like this. I like that one. Sometimes we give a bonus point for that one. With a polynomial here, it's not a rational polynomial, so we're not going to get any vertical or horizontal asymptotes. Let's just jump right in and calculate some of the important points that we can look at from this. An easy point that we can get is the Y-intercept. So to find the Y-intercept, what do I need to do?
Set x to 0.
Good. Set x equal to 0. And if I set x equal to 0, what do I get for y?
Negative 2 over 3.
Thank you. Negative 2/3. The rest of the information that we're going to have to get by looking at some derivatives. So let's start by calculating the first derivative. Y prime is going to be negative 1/3 times what? 3x squared minus 3. Nice. And let's simplify that a little bit. If you distribute the negative 1/3, you'll get negative x squared minus 1, or plus 1. While we're at it in the mode of calculating derivatives, let's calculate the second derivative. What's the second derivative? Nice. Negative 2x. I want to know where these derivatives can change signs. So let's work with the first derivative. Negative x squared plus 1. So this can change signs when this actually equals 0. So that equals 0 when 1 equals x squared, moving this to the other side. Plus or minus the square root gives me x is plus or minus 1. That's where the first derivative can change signs. Let's make ourselves a little table. X, y, y prime, negative 1, and 1. So we need to test some points here. I would suggest points, keep them simple, negative 2, 0, and 2. Those should work pretty friendly. Should be some easy points to test. So I don't think we need to take out our graphing calculator to test these, do we? If we're testing our first derivative to figure out where it's positive and negative, let's plug in a negative 2 here. Be careful, you have to square that. Negative 2 squared is 4, and then take its opposite. So you get negative 4 plus 1. That would be negative. It's negative 3, but the important thing that we need out of that is that it's negative. Pretty easy to test 0. What do we get when we plug in a 0 into... Yeah. So negative, positive, and then negative again. What's that telling us about our function? It's decreasing, increasing, decreasing. Let's use this little chart here to determine some of the nature of our points at negative 1 and 1. Now the derivative is 0 here and here. That means these are critical points. Interesting things usually happen at critical points. What kind of a critical point is negative 1? What's happening at the graph there? Yeah, a local min. The graph doesn't get any farther below any point nearby. So this is a local min. And over here at 1, a local max. We're going to come back in a little bit and fill in these two values right here. Or we can fill them in maybe up above. Doesn't matter. Let's keep going. The next point that I want to take care of, or the next thing that I want to take care of, is the second derivative. So less work for the second derivative, because there's only one point where that can change signs, and that's at x equals 0. At x equals 0, the second derivative is 0. The function itself is also 0. So for y equals negative 2x, let's test some points to the left of 0 and to the right of 0. To the left of 0, what's the sign of the second derivative? Positive. So that means it's what? Concave up, and then negative, concave down. Now there's 2 points here that it'd be nice to know the coordinates that go along with it. That is the y coordinates, because we're eventually going to have to graph this. So it's up to you exactly how you want to find those. I'm going to put them in a graphing calculator just because I'm feeling a little bit lazy. That's not quite accurate. It's actually economy of movement. So let's put the function in. Now with your newer ones that are updated with math print, you can get fractions if you hit the alpha key and then the y equals key. The first one allows you to put in just a regular fraction, so let me do that. Negative 1 divided by 3 times parentheses. Now the rest of the function was x cubed minus 3x plus 2. So that's kind of nice. It avoids having to worry about parentheses and other oddities involved entering in the function. Let's go to the table. Now there's 3 points that I want to find the coordinates for. I want negative 1, 0, and 1. And notice the way I've done this. It gives me nice fractional values. That's great. You can set your calculator up to get decimal values out of this as well. I like the fractions. So at negative 1, I get negative 4/3, and at positive 1, I get negative 2/3. At 1, oh yeah, you're right. I'm sorry. 1, you get 0. I looked at 0. At 0, yeah, you're right. At 0, we get negative 2/3. Thanks, Tiffany. All right, so let's keep a little chart here. At 1, actually at negative 1, we get negative 4/3. And at 1, we get negative, no, at 1 we get 0. Okay. Cool. Let's put these together along with a graph. So let's draw ourselves a graph. You can borrow a ruler if you'd like. Now I haven't graphed this beforehand, so I don't know exactly what it looks like, but I should be able to come fairly close based on the information that we've got here. So let's see how we do. I'm going to give myself a generous amount of space for these things. So I'll put my tick marks an inch apart. Let's start by plotting the points that we know exist on our graph. We've got one at 0 and negative 2/3, so that's about here. At negative 1, we have negative 4/3. That's about down here. And then at 1, we have 0. What else do we know? Well, we know it's decreasing until it gets to this point. We determined that from our first derivative. First derivative says it was decreasing until it got to negative 1. So from negative infinity to -1, it's decreasing. It's increasing from -1 to 1. So increasing from -1 to 1. And finally, it starts decreasing again at x equal 1. So 1 to infinity. So it's decreasing until it gets to this point, then it's increasing, then it's decreasing. The other thing we want to take account of is the concavity. It's concave up from negative infinity to 0, and concave down the rest of the way from 0 to infinity. So let's make sure our graph matches all this information. So something like that to the left of the y-axis, and then to the right of the y-axis. You might notice that I'm not really taking time to plot a lot of points. I want the big features, the general shapes. I'm not interested if this passes through 2 and -1, or if it passes through 2 and -1.1. I mean, I don't care. I'm not going to take out a magnifying glass and look at your graph. I want to see the general shape reflecting the calculus that we've gone through here. So how does that look? Let's compare that to the graph that we can get by simply looking at our equation on our calculator. So from, say, -2, so I'll set up my window from -2 to 2. And, all right. So I need to adjust the window a little bit in the y direction. I have it too smushed. So let's go from -2 to 2. That looks pretty good. So it should just kiss that x-axis and then head down. Exactly what we've got. Twins. Anything on problem 16? Kind of our warm-up problem on this.
How come we didn't worry about any like asymptotes or anything?
It's a great question. In order to have a horizontal asymptote, you have to have a limit as x approaches infinity or negative infinity that's finite. I mean, something other than infinity or negative infinity. If you take a look at the limit as x approaches infinity of this graph, it's going to be negative infinity. If you put in bigger and bigger values, you can see that based on the form of the graph. This is just going to keep going down. On the other side of things, as you approach negative infinity, it's going to go towards positive infinity. So there is no asymptote. You get vertical asymptotes where the denominator is 0. But there's no denominator here. Or at least there's no denominator that can equal 0. So it's a great question. There's no vertical nor horizontal asymptotes. You should look for those things first because a lot of times that'll frame the graph. And you should draw those features in before you draw in anything else. But in this case, we didn't have those. So thank you. Anything else? Still kind of nagging you a little bit about problem 16 here. That's not a bad idea. You know, and in practice, maybe you'll do that at home. You know, here, I guess I like doing it the opposite way. But yeah, there's nothing wrong with starting out looking at the graph and go, okay, I should expect these kind of features, you know. So that way, when you calculate a second derivative and your second derivative says, well, wait a minute, the second derivative changes signs at 1, and you look at the graph saying, wait a minute, this changes from concave up to concave down someplace other than 1, that you can catch mistakes. So it's not necessarily a bad idea. It's just, I don't know, here when I'm teaching it, I like to see that our calculus eventually matches that. But no, in practical terms, yeah, it's not a bad idea at all to start with the graph. Okay. Let's try problem number 12, unless there's anything else. Now, problem number 12 is kind of challenging. So I think we'll calculate the first derivative together, and then I might just give you the second derivative. That's not necessarily a bad thing. What can happen is that if you make a mistake in calculating your derivative, then you can be kind of screwed the rest of the problem. So, I'm not adverse to giving you little hints or giving you some help on these things, because I don't want to see you get the rest of the problem wrong because you made a tiny mistake on the derivative. Okay, so problem number 12. Zoom out a little bit. There we go. F of x is x times the square root of 9 minus x squared. All right, a lot going on in this one. First thing we have to consider with all these problems is the domain. There's a limit on the values for x. You can't just put in anything. Somebody throw out a number. Any number. -3. If I put in -3, I get 9 minus, well, -3 squared is 9. I get the square root of 0. That's not a problem. But what about, go ahead, James. -4. 9 minus 16, square root of -7, that's a problem. So I can't just throw in anything and everything. I got to make sure that 9 minus x squared is greater than or equal to 0. Now that means 3 minus x times 3 plus x is greater than or equal to 0. That tells me that I kind of have limits on things. 3 and -3 are where this equals 0. Now, are the limits going to be between this or outside of this? Which area is going to be part of my domain? Between. Good. Because as long as your number is between -3 and 3, you can put it in and square it and still have something which is less than 9. In other words, that difference is going to be positive. So there's your domain between -3 and 3, and that's it. When we graph this thing, the function won't exist outside of those numbers.
From your example of x equals 4, 9 minus x squared is greater than 0.
Well, let's try it.
Oh, no, it's not. I'm thinking wrong.
Okay. All right.
It's a negative number.
Yes, and that's the problem, because we'd end up with the square root of a negative number. I'm not sure if any of you can see this, but this is an odd function. You can go back and double check these. Odd function. Visually, it's not as striking as an even function. An even function is symmetric with respect to the y-axis. That is, if you fold it around the y-axis, it's like a mirror. The function will land on itself. But odd symmetry, it's a little bit tougher. Reem, are there going to be any vertical asymptotes here? No, because there's no denominator, right? So there's no denominator, there's no vertical asymptotes. There's actually no asymptotes at all, really. So the next thing we're going to work on is the calculus part of this. Let's work on finding some derivatives. I'll rewrite this as x times 9 minus x squared to the 1/2. When we differentiate this, we're going to have to use a combination of two rules. One's the product rule, the other is the chain rule. Well done. So f prime of x, derivative of the first is going to be 1 times 9 minus x squared to the 1/2 plus the derivative of the second, which is 1/2 times 9 minus x squared to the minus 1/2. But that's not where the derivative of the second stops, is it? What else do I need as part of the derivative of this term? Negative 2x. Derivative of the outside times the derivative of the inside. So the derivative of the outside, you bring the 1/2 out in front. Subtract 1 from the exponent, times the derivative of the inside, times x. Remember, it's f prime g times g prime f. So don't forget about the x there. A lot of cleaning up to do here. So the first term, just 9 minus x squared to the 1/2. For the second term, the 2 and this 2 cancel each other out. What else is left though? What am I going to write in front of the 9 minus x squared term to the minus 1/2?
X, negative x.
Go to negative x squared. Now, I would suggest that if you had to work with this in any way, that you'd probably want to clean this up. And we've gone through a few like this before. You'll see some others in other videos that I'll post online. And that is, let's factor out this term with a fractional exponent, this negative fractional exponent. So when we do that, I'll have 9 minus x squared to the minus 1/2. Now when I factor that out, this term, 9 minus x squared to the minus 1/2, thank you. You were just waiting for that. No, I appreciate that. Yeah. No, I was kind of in the zone. I wasn't even looking here. No, thank you. So 9 minus x squared to the minus 1/2. That's going to divide each of these terms. So 9 minus x squared to the 1/2 and minus x squared, 9 minus x squared to the minus 1/2. Now, if you can do this step in your head, power to you. I show it because it's tough to get this factorization and this simplification. So I don't want to lose anyone while I do this, but if you can do this in your head, that's great.
That's why you show that you divide it, because it's hard to see what's after
Yeah.
you took out that.
It's not too many people that can look at this and say, oh, I factored that out. I'm left with 9 minus x squared minus x squared. I mean, if you can, great. But let's see what happens here. Those two terms cancel out altogether. These have the same base. And when you divide things with the same base, you subtract their exponents. If you're very careful, what are you going to get for the exponent here? A 1. So overall, we're going to have 9 minus x squared to the minus 1/2 times 9 minus x squared to the first power minus x squared again. Whew. Past the hard part. Inside here, I don't need the parentheses to the first power, so I'll just move these terms around. There's a like term here and here. I'll rewrite that as 9 minus 2x squared over 9 minus x squared to the positive 1/2. So I did two things here. I took this term into the denominator and I made the exponent positive. And then I took and combined the like terms here and here to get the minus 2x squared. That's my first derivative. So that's f prime of x. And from this, I'm going to want to know where the first derivative equals 0 or is undefined. Because at those points where it equals 0, the numerator is 0, or where it's undefined, that's where the first derivative can change signs. So let's take a look at both of those. Basically, it's where the numerator equals 0. 9 minus 2x squared equals 0. And where the denominator equals 0. 9 minus x squared raised to the 1/2 equals 0. For the numerator, I'd move the 2x squared to the other side to make it positive. And then use the square root property. Plus and minus the square root of 9 over 2, which is plus or minus 3 over the square root of 2. You can rationalize that if you want. This is not an algebra class, so I'm not really going to worry about it, but I will do it here for you. 3 square roots of 2 over 2. It might be just as easy to find a numerical value based on the square root of 4.5. It's probably the easiest thing to do. For the denominator equals 0, well, the easiest thing to do here is get rid of the square root. Square both sides, get 9 minus x squared equals 0. Get plus or minus 3 equals x. I think I can figure out what's going on at plus or minus 3. Here, we're going to have to figure out a little bit more. Let's put those points into a little chart and see what's going on with the derivative. There's a lot of points here to take care of. So we got points at x, f, and f prime, at negative 3. I'm going to go with this one. Negative square root, or negative 3 over the square root of 2, 3 over the square root of 2, and finally 3. Well, there's one thing that we should keep in mind about a couple of these points. 3 and negative 3 are at the edges of our domain, aren't they?
Isn't it 3 square root of 2? Oh, okay.
I just chose a different form of it. You're right. You're right. But it can't change signs to the right of 3 because 3 is not in the domain. Same thing with negative 3. So really, all we have to do is test a couple points in here. Actually, these 3. So an easy one to test would be 0. This one, I think we can test 2 and negative 2 into our derivative and see what happens there. These are kind of messy. I would suggest that in testing these to decide their sign, that we pick up our calculator and program the derivative into our calculator to do our test points. And this went off again. So let's program our calculator like that. You've got two choices. Either you can put the numerator in parentheses, or you can use some of the fancy keys that your graphing calculator offers. So I'm going to use some of the fanciness that my graphing calculator offers, but there's nothing wrong with putting 9 minus 2x squared in parentheses. Hit the alpha key, then the y equals key. I'll choose to do a fraction. It's 9 minus 2x squared over something to the 1/2 power is like a square root, 9 minus x squared. Let me make sure that my table is set up to ask. It is. Let's just go to table and test some values at -2, 0, and 2. And I'll delete the rest of the values that I see here. Looks odd. It's always positive. Why not? They're in the domain. Oh, are they? Are they? Really? Oh, it's. Oh, okay. Thank you. All right, so let's use 2.5 and negative 2.5. It did look suspicious. I probably should have calculated that first. -3 divided by square root of 2 Yeah, okay. So that was my problem, is that 2 and negative 2 weren't big enough. Negative 2 wasn't to the left, and positive 2 wasn't to the right of these. So, thanks, Kurt. So let's go back to our table. Negative 2.5, 0, and 2.5. There we go. Okay, what's the important information that I need from this table? The signs. Negative, positive, negative. All right, so negative, positive, negative. Decreasing, increasing, decreasing. What kind of points are these? Starting with this one.
Yeah, min and max.
Good. That one's a min. This one's a max. All right, let's actually find out the coordinates for these points. That's not necessarily a whole lot of fun. Those points are really the square root of 4.5. So what you could do quite easily on your calculator is type in square root of 4.5, and then let's exit that. Store that in x. Now what the function asks us to do? The function asks us to take x times the square root of 9 minus x squared. So let's do that. X square root of 9 minus x squared. Oops, didn't get the 9 in there. 9 minus x squared. Thank you. There we go. And you get back to 4.5, which is ironic. So your coordinate points there are 4.5, square root of 4.5, and 4.5. This is an odd function, so we'll also get negative square root of 4.5 and negative 4.5 as well. So we'll get those 2 points. Yes? That's 9 over 2. So, yeah, I was just being lazy. I didn't feel like typing in a big fraction there. All right. Like I said, these problems can get kind of long, especially if you have to calculate all the derivatives from scratch. So let me help us out a little bit. The second derivative. So f double prime of x, is 2x cubed minus 27x. And that's over 9 minus x squared to the 3/2. Again, I want to know where this can change signs. This can change signs where the numerator equals 0 or the denominator equals 0. Well, the denominator equals 0 the same place the last one does, which is 3 and negative 3. There's not much that's going to happen because those points are at the edge of my domain. So let's figure out where the numerator equals 0. So that's 2x cubed minus 27x equals 0. Let's factor out an x. That leaves behind 2x squared minus 27 equals 0. Can anyone see one spot where this equals 0?
0.
Yeah, when x equals 0, right? You've got something times something equals 0. Either x equals 0 or 2x squared minus 27 equals 0. Now there's good news coming up here. If you solve you get x is plus or minus the square root of 27 over 2. Now what's good news about that? It's not in the domain. Yeah. If you look at this, it's plus or minus the square root of 13.5. And I don't know exactly what it is, but since that's bigger than 9, it's going to be outside the domain. So we don't have to worry about these. So another good point for figuring out the domain. Really, there's only one point we have to worry about, and that's x equals 0. X, f prime. Zero. Let's draw ourselves a little box. Here we go. And we need to test points in our second derivative. So we figure out where it's concave up and concave down. I don't see anything wrong with -1 and 1. Now the sign of this is going to be determined pretty much by the numerator, because the denominator is going to be positive throughout the domain. So let's just look at this when we put in a -1. If I put in a -1, let's see, it'd be negative and a positive. So -2 plus 27 would be positive. If I put in a +1, I'd get a negative here.
Why did you put in the numbers from the denominator?
Because I happen to know that this, no matter what you put in here, in the range of -3 to 3, this is always going to be positive. So it's a good question. I was just kind of taking a shortcut. Yeah. There's nothing wrong. Your calculator will tell you the same thing. If you put in the whole thing, you're going to get, positive and then negative. And the important thing for us is what here? What's it telling us about our graph? Concave up and concave down. Whew. All right. Yeah, I kind of cheated. I knew that this was going to be, the denominator was going to be positive, so that ultimately the sign of this, the second derivative, is going to be determined by whether or not the numerator is positive or negative.
Okay.
So, yeah, I cheated a little bit. Sorry. I won't do it again. I think we've got everything here now. So, flip over your handout. Let's see. We've got a couple points that are already drawn for you. This one here and this one here. That's the square root of 4.5 and negative the square root of 4.5. This is going to be your min, and that's going to be your max, respectively. I guess there's one more thing that we should have probably looked at. I can look at it quickly enough with you. F of x was x times the square root of 9 minus x squared. We didn't take time to find the x-intercepts. The x-intercepts are when y equals 0. And we can kind of see one of those right off the bat. And that's x equals 0. Or square root of 9 minus x squared could be 0, which is 9 minus x squared equals 0, squaring both sides. And that equals 0 at what points? 3 and -3, thank you. X equals 3 and -3. So we've got all these points for x, -3, 0, and 3, where y equals 0. So that's here and here. Finally, let's play connect the dots. You've got a nice function that is decreasing until it gets to this point. Then it's increasing and decreasing. It's a little bit better here. concave up, then concave down, minimums, maximums. It's got it all. So, whew, get out the oxygen bottle. Yes, sir.
Would you accept x equals plus or minus in the test?
Oh, yeah. Yeah, no problem with that. There's another hand up? No.